Who would like to volunteer to be a note taker? It is fun and exciting.
You have to let me share the screen. Do I have to request it?
Okay, there you are.
Okay.
Let's see. Yeah, I think you have requested actually.
Okay. I'll do that. Let me bring up the thing
Yeah.
first. Okay.
Okay, I see you requested it now. So, or maybe it's Lenny that has to, let's see.
Lenny, could you accept my request to share the
Yeah.
whiteboard?
I'm pushing the grant screen. Oh, do I have to stop? Maybe I have to stop myself. There.
Okay, it should only take a second.
Yeah, I think it might be working now. Let's see.
Okay, folks, while Dino demos out his demo and his dry run.
The GAP protocol. Oh, shoot. It doesn't stay going. It stands for Group Address Allocation Protocol, and it's a way for applications to get a unique group address across the network and be able to rendezvous receivers and sources. I'm showing 5 nodes here. You'll see the 3 receiver nodes on the right-hand side. They're going to run an application called GAP Receiver, which they're simply going to join the group that hashes from the group name PIM-MBONED-group. Does that sound better from you, Lenny? Let me start this one up.
That sounds pretty good.
Is joined. Good.
The screen is on inception mode.
And I'm going to join it. Join receiver 2 and receiver 3. I know what to do. Waiting for messages to come in.
All right, cool. That worked. So we're about ready to get started, but we need a note taker. Who would like to be the note taker? Just a reminder, we cannot.
Nate's volunteering, but he wants some direction on what he needs to do.
Just take, write down high level, semi-important things. How else would you describe the role of note taking? Do your best. That's all I can say. We do have transcription. We do have video, so it doesn't have to be exact. But you know, the high points. So Nate, are you officially in?
All right, he is in.
All right. Okay. In that case, we can get started. We'll wait 1 more minute for folks to come in. Okay, we can get started. So welcome to MBONED. Here's the note well. You've probably seen it a few times this week. Please be aware of it. Please review it, and please note it well. In terms of meeting tips, for those of you who are in the room, we do ask that you still sign into Meet Echo, and let's use, it doesn't look like we're going to have a lot of chaos at the microphone, and I don't think Stig is going to have to be breaking up many fist fights tonight, looking at the size of the room, but Please do use the Meet Echo to join the mic queue, even physically on site, just in fairness to the people who are off site. Because last meeting we had a bit of a contention issue where we had people patiently waiting online in the queue, and they were skipped ahead by folks who were in the room. So we'd like to avoid that. For those of you who are in the room, please do wear a mask, just like you have been all other working group meetings. And that's the usual stuff. Okay, here's our agenda. Anything to add? Any additional bashes to the agenda? Anything we missed? Okay, we actually should be able to finish early, get out of here early. Kind of a light agenda this time. And let's jump straight into the status of working group documents. The first document to discuss is the telemetry draft. That is currently in working group last call. It's scheduled, working group last call is scheduled through the end of this week. We have not heard enough folks to support advancement thus far. We have heard from 0 non-authors in support of advancing this draft. So if you'd like to, so first, we'd encourage folks to read the draft. And second, if you do support advancement of the draft, please speak up. Or if you have any comments, or if you don't support advancement of the draft for publishing, please do speak up. Yang Models draft, is Sandy on the line, or any of the other authors from that draft? Any updates on that one? I think the usual update is looking for feedback from folks in the working group. And the redundant ingress failover draft. Do we have any folks online who are co-authors of that one? Yes.
Hello, Jenny.
Hey,
Sandy Zhang
how you doing?
ZT.
Hey,
Yeah,
Sandy.
hello. About the Young model and the redundant ingress failover draft, we'd like to update a new version for it, and maybe we will present in next meeting and call for working group last call. Okay.
Great, thank you, Sandy. The other drafts are Jake's multicast to the browser documents. They have all expired. Jake has been reassigned to different work and is not able to devote further time on these docs. So if no one, they're kind of looking for someone to take over. So if anybody is interested in taking over these drafts, please let us know. Otherwise, they may fall by the wayside. Other documents, there's an AMT Yang draft that Yishang will be discussing next. And let's see what's up. Yishang, if you would like to, you're up. Would you like for me to drive your slides, or would you like to drive the slides yourself?
Can I control the slides? I have asked.
Sure.
Yeah, I'll choose. Yep. Hello, everyone. I'm Yisung Liu from China Mobile. Today, I will present the MT Young model. This is the second time for this draft. Last IETF, I have introduced the MT models configuration and the state information. And this time, we updated for the version 2 to add the MT statistics. Sorry. Firstly, we add some statistics of the specified MT tunnels on the MT relay side, like in the slide. Secondly, we add some message for both the receiving message and the send message on the MT relay. This slide shows that we also add some error message statistics on the MT relay side. Okay. And the next is that for the MT gateway side, and we add some message statistics of the specified pseudo interfaces. And this the MT gateway side for the sending message or both the sending message and the receiving message statistics. And this statistics information or a reference from the implementation from some vendors. Now, this draft covers MT configuration and the state information and the statistics information. So I represent the co-authors to ask for the working group adoption. That's all. Thank you.
Great, thank you, Yishang. Anyone have any questions? Has anyone, let's do a show of hands. Who has read the So we're gonna start a question, a poll on who, please raise your hand if you have read the draft. Okay, looks like we have about 5 folks who've read the draft. Okay, next poll question is, let's see here. Oh, how do I end this thing? All right, there we go. So 6 folks have read the draft. And now the question is, an unofficial polling poll. Who supports adoption? Let's see. Who do you support? Okay, there's a second the second poll question. Okay. All right, it's numbers are trickling in. All right, so it's 9-0 in support of this. So we'll take this to the list, but do encourage folks to read the draft and provide the authors with any feedback and comments. And looks like we'll start an adoption call on the list shortly. Thank you.
Thank you.
All right, Dino, you're up.
So when I start the demo, well, I guess the mic will stay fine there.
Yeah, yeah.
Hi, my name's Dino, and I'm going to talk about a new protocol that we just developed recently called GAP, Group Address Allocation Protocol. And it was inspired by a lot of the use case and discussion with Nate for his marine network plug and play sort of requirements. So we're trying to build something that's a general group address allocation protocol for the network layer, and the network layer and multicast applications don't have to depend on a third-party entity like at the application layer to figure out what the group address is. So it's a network layer solution that's probably been needed for a long time. So we're give a shot at a new idea. Next, please. So what is GAP? The goal is to make it totally decentralized and make it a group allocation protocol that's allocated by members that might want to be part of a group, receivers, multiple senders, or whatever. So there's no central entity to allocates addresses. And of course, we want to allocate addresses in a unique manner. So so the groups don't inadvertently merge to each other, and multiple groups that are different don't collide at layer 2 in snooping switches. Group addresses are allocated and guaranteed to be unique across all the GAP speakers. And the nodes don't have any zero configuration other than specifying at the application a group name that they need to rendezvous with. So the protocol will allocate both IPv4 and IPv6 group addresses, and the group addresses won't collide, as I mentioned, at layer 2. So we could allocate uniqueness in an IPv6 group address up to 32 bits because that's what will fit into an IPv6 MAC layer address, and up to 23 bits for an IPv4 address. Should work on a single subnet as well as a layer 3 infrastructure, and it should also a layer 3 infrastructure that supports native multicast, but also that where the native infrastructure doesn't support multicast, you can use overlays to realize multicast for the multicast applications. It can coexist with other group allocation protocol by using an IANA gap allocation block. So the idea was to go to IANA and request an allocation block that gap addresses will hash to, and also request a single multicast address so the gap protocol could run on that. And of course, when multicast is not available, use multicast capable overlays. How does it work? Well, multicast source and receiver nodes participate in the GAP protocol. They want to be able to join or send to a group. So they will request the GAP protocol that runs on their system, actually in their application space to run the protocol. The application will specify a group name, and all the applications that specify the same group name means they want to join to the same or send to the same multicast group address. The way it works is that the group address is a hash of the group name using SHA-256, and we try to find a unique address with those with that hash. The GAP nodes then send, after the hash, they send claim messages to verify that this address is unique, and the claim message is a group name, a group address, and a timestamp of when the group was created by the first member or sender. Claim messages are sent every 1 minute, so we're trying to minimize messaging here. If a node is part of a group name and receives a claim for the group name, it resets its 1 minute timer. So we only have, among all the group members and senders, there's only going to be one GAP claimer at any given time, and it keeps changing because the 1 minute timer is relatively random within a 10% range, plus or minus 10% range of the 1 minute timer. If a node uses a group address found in a claim message for a different group name, that's defined to be a collision. So if you have group name A and group name B, if it happened to hash into the same group address, one of them has to resolve it, and the claim process does that. So if B comes later, sends a claim message for this group address, and A says it sees a collision, A will trigger a claim message, and B will reallocate, do a #+1 to build a new group address for this group name. And we do it up to 4 times. So you use the group name, and if there's a collision, you do group name +1. If there's a collision, you try +2, and then you try +3, and then you give up. And you can tell the application that there's no group that you can allocate. And then other procedures have to be done, like pick a new group name. So when a protocol or a network partition occurs, not all the app nodes will be able to see claim messages. So in the case of A and B came up and they weren't able to communicate with each other, they would both hash to the same group address. The applications would start sending and receiving from it. And then when the partition healed, then there's a conflict in the group address. That's no different than somebody coming up for the first time doing a claim with a collision address, and A would send a claim and tell them to do the +1 thing. And whenever a group address changes and the application is already started up, the way the API works is that there's a callback function to the application where if a group changes, you can call the application back, and then it knows that the group changed, and it can actually IGMP join or MLD join the new group or start sending to the new group. So the point about protocol scales, there's really only one claim message per group name, regardless of the number of nodes that are using the group. And there's only one, at most one claim, triggered claim, when the collided group is detected as well. Collided addresses are not used and converge quickly since collision detector triggers claims. So it's something that happens pretty quick, a sub-second, at most 1 second. So all the messages are encrypted. We decided to use Cha-Cha-20 cipher because it's pretty simple. Uses a shared key to encrypt and decrypt claim messages. The GAP protocol has a single message. It's called the claim message. Right now, the default key is the group name. So everybody that wants to send claim message could use the same group name. If there's multiple group names running at the same time, you have to make sure that if all those GAP speakers are running, that they need to use the same encrypted. My implementation uses the group name right now because it doesn't want to configure anything. But really, what you need is a well-known encryption, a well-known key that all group members use because they're going to be joining different group names. And you could run in hybrid mode. You can do both. There's a marker in the message where it tells you if you don't see this marker in the message, it means you couldn't decrypt it, and so you just drop the packet. If it comes in plain text, you'll see the marker without trying to decrypt it for your when you're not using a configured key. The protocol can detect bad actors, which is important because we don't want the GAP group to be signal jammed. So if they're sending too fast or forging a timestamp or creating bad hashes from the group name, you put it on a local list and start ignoring it. And if necessary, and we're going to do, this is work in progress, if there's too many bad actors, K out of N are bad actors, we can rekey to exclude the bad actors. So the good guys can talk and the bad guys can't hear it, so they can't get involved in, because if the bad guys see the messages, they could try to do bad things. And so if you encrypt it by rekeying, it'll be a cat and mouse game, but we'll try to solve that problem. But that's work to be done, and we'll report at future IETFs how that's coming. Now, if you're running GAP over an overlay, the actual, at least for the Lisp overlay, the mapping system can decide who comes and who goes. So if GAP sees these bad actors doing things, you can tell the overlay to not send packets, not have that guy send packets anywhere, and you've actually pushed the problem all the way back to the source. So you don't have, because if the bad actor is going to send a multicast group, everybody has to receive it and throw it away. But if you can tell the overlay to not let them send at the encapsulating router close to where the bad actor source is, you could stop him from sending packets. So it's a good solution to not have him, DOS attack the GAP group. And you could actually regroup, do the regrouping too. If everybody hashed, let's say, to the +1 for this group name, and you see that that group is being DOS attacked, you could switch them all to +2 pretty easily.
But more protocol specifications are required for those sort of things. These are the kind of things we have in mind that could go wrong with the protocol, and we have to decide if we should address them or are they rare occurrences. So that's TBD stuff. So since GAP is pretty lightweight, doesn't send very much, simple processing, the most CPU it uses is probably decrypting and encrypting the packets. But SHA-256 is pretty lightweight. It's additive and exclusive OR based. It's not polynomial based, so it doesn't take a lot of CPU to encrypt the packet. And the message is relatively small too. I think it's less than 75 bytes or something like that. So we decided to have GAP run inside the application process space, and there's 4 API calls to the protocol. So you open up the API using the init call, and you provide a callback function. So if the group does change, you can take action. And when you need a group address, you simply call allocate with the group name, and you get returned back a multicast address, V4, V6, or both. And then you use it to join or send, depending on what instance of the application is running. And then when you're done with it, you can release it. Releasing it just means that this node doesn't have to GAP claim it. If it sees a collision and it's not part of the group name, it doesn't have to participate. It's only the guys that are joined to the group name that participate in the collision detection. And then closing the API means the GAP protocol shuts down in the application. Usually it's going to happen because the application is going to shut down because it's done doing what it needs to do. Apps which participate in the same group are started with the same group name. Apps can use multiple group names since they may have requirements for multiple group address use. And a lightweight app can use a lighter weight RESTful API to a GAP proxy node that runs the protocol. So if you have an IoT device and you don't want to run the protocol there, the GAP allocate call could actually do a RESTful call to do an allocation in another node that's running the GAP protocol. And it could be a standalone node, which we hope it doesn't because it looks centralized then, but it could be another node that's participating in it as well. What's unfortunate about the RESTful API is you have to point it to something, and that causes configuration and centralization. So we're trying to decide if that's going to be useful. If it's lightweight enough, we have to look at the implementations. The implementations will be done in Python and C, and we'll have to see how fat that would be in an IoT type device. So I did an implementation, and I did it in Python, and I built a couple of applications. The application I built was really simple, just to showcase the protocol and just to send messages. So the sending application is an echo server or echo source, and I called it ES. And then there's a echo receiver. And simply what they do is when you type them on the command line, you specify the group name, and the echo source will send a message. And the echo receiver will simply hash the group name using GAP, IGMP join, and wait for that message to come in and display it on the console. So pretty simple. And I'm going to do a demonstration of it in about a minute or so. Then we have a monitoring tool called GAP Shark, which they could listen on the GAP group on a particular group name or everything, and it's like a Wireshark equivalent, so you can debug the protocol. So that was used as a tool for me to develop the protocol. And there's utilities, GAP hash, GAP scale, GAP collide, to do various things to help debug things. Okay, so I have 2 demos. The first one's pretty short. It's only a minute or so. And it's just a very high level, just showing you ES and ER running. And then we also have a protocol demo where we can go deep dive under the covers and see how GAP works, show how the hash works, and how in the case where there's no collision. And then we're able to use a scenario where we can make a collision occur, and we'll see that it gets resolved. The environment is, I'm just running this right now on my laptop, running in Docker. So the Docker bridge is going to provide native multicast connectivity, single subnet multicast connectivity. And the 3 nodes on the right-hand side are the 3 receivers, and the 2 big windows are going to be where the senders are. So we're going to, it's a movie that's going to play. We're going to go ahead and put the mic up to it, and then I know it's a little bit hard to see those characters, so I'm going to try to zoom in where the focus goes in the windows. So,
I have a question. Do you want
Yeah,
to do it
yeah.
now? Or?
oh, go ahead.
Yeah, so Stig. So I see in the message format you have both a V4 and a V6 address field.
Yes.
So are you expecting that you will allocate both of them at the same time, possibly?
Yeah, I was
or-
thinking at least for the first try, allocate both of them at the same time,
Yeah.
and then maybe that group address that's returned is an array of two
Yeah.
elements or something.
Yeah, I'm asking because, for most or all the multicast protocols we have today, we generally send separate V4 and V6 messages where whatever is in the payload is kind of reflecting the address versus the message itself, right?
Yeah. Yeah.
Right. I mean, like an IPv4 PIM message, right?
Yeah.
It's sent to an IPv4 destination address.
Yes,
And
correct.
it contains only V4
Addresses. Yeah.
addresses.
Yes.
But in theory, I mean, we could have done it differently. And
Yeah. Well, what I wanted to
Yeah.
do was I didn't want to be address family proactive. And so it's really supporting a multi-address family implementation. So you have a group name, you get two addresses, you decide if you want to use V4 or V6.
Yeah. I was wondering slightly if you use the same hash, I mean, it will be the same 32 bits or 23 bits, whatever, right?
So I think I haven't done the V6 portion of it yet. It's just
Yeah.
simple matter of writing code, but I was going to return 32 bits of uniqueness for V6 and
Yeah.
23 for.
Yeah.
Yeah.
Yeah, I was wondering slightly if you could, what should I say, just get like unique 32 bits basically, and then use that
For both.
the V4 and the V6 address.
Yeah, but it will end up colliding for layer 2 switches, so we have
Yeah.
to be careful
Yeah.
because we have the 28 to
Yeah,
23-bit
sure.
mapping problem.
Yeah, so one way would be to allocate 23 bits that are unique, I guess, and use that for both V4 and V6.
Yeah,
But,
right. That was kind of the plan. Yeah.
yeah.
Well, the thing is, we could certainly do that, and then the higher order, the other 9 bits or whatever would not be used for V6. But the thing is if we use 32 bits, we have less likelihood of collisions.
Yeah.
So
one thing I think
we have 4 bytes of MAC address that we can use.
Yeah. One thing we maybe should think about is today we have like 31 bits that basically are used by Madcap, right?
Yeah.
And there's no other dynamic protocol. So we should maybe think about, is it worth splitting that into like smaller spaces where each protocol can get their own 28 bits or whatever? Right?
Any allocation protocol can?
Yeah,
Or-
so I'm thinking basically, let's say if you split the 31-bit space into say like 8 or 16 blocks, right? Then you could have up to 8 or 16 different assignment protocols that each have their own space.
Yep, we can do that.
So
You think it would be better to do that than ask IANA for more, is what you're saying?
Yeah, so today it's like you have 32 bits and half of it is for static config, right?
Yeah.
And the other 31 are for dynamic.
Yes.
So we can't really, I think, extend the dynamic, into what is static today.
Oh, I see. Okay.
Maybe we could, but
Okay.
but the other option is to split it.
I think
into
whatever you think
smaller
is
chunks.
the best to do that. And I don't know if I need to specify that in the gap spec, but I do need, I should write some text about what is the uniqueness with. So because, and should it be consistent? So it's something for us to think about.
Yeah, so it could potentially be a separate document that kind of
For
takes care of splitting up the space.
to
and
give
stuff,
recommendations
maybe,
to allocation
perhaps.
protocols. Yeah. Okay.
Just one more thing.
Yeah. No, go ahead.
I see that you for V6 you used link local scope in the draft.
I did.
It's like FFO2.
Oh, okay.
So,
Yeah.
So I was thinking a bit.
That wasn't in. That was a mistake, not
Okay,
intentional. Yeah.
So one possibility is to make it like scope variable
Site.
scope, right? So
Very
you
good.
can once you get the allocation, you can use any scope.
Uh-huh.
But the problem is you need to make sure maybe that the GAP protocol works over the entire
Different scopes.
scope, right?
Right.
If you do link local scope, it's fine if GAP is just on that link.
I didn't mean it to be link local scope.
Yeah,
I
yeah.
should have used FF01
Yeah.
because if you need to use link local, you could still use an FF01
Yeah.
address. Okay.
Yeah.
So I'll fix that.
Yeah.
That's good.
But yeah, I may need to think a little bit about how scoping works.
Okay. Sounds good. Okay.
Yeah. Okay. Thanks.
Good. Yeah. Great comment. Okay.
Nate?
Nate from Garmin. I just wanted to add to the discussion that Dino and Stig had about the allocation blocks for multicast addresses. Dino, I sent you kind of a document about that, and I'll forward that to you as well, Stig. So
Thanks. Okay. So.
Any other questions for Dina?
Other questions for Dina? Other questions for Dina? Other questions for Dina? Other questions for Dina? Other questions?
Okay. Ready for the demo?
Oh, fire away.
Yeah. I need about. Do I have time, Lenny? I need like about 10 more minutes.
Sure.
Okay.
You got it.
A demo of the GAP protocol. The GAP protocol stands for Group Address Allocation Protocol, and it's a way for applications to get a unique group address across the network and be able to rendezvous receivers and sources. I'm showing 5 nodes here. A demo of the GAP protocol.
Sorry.
The GAP protocol stands for Group Address Allocation Protocol, and it's a way for applications to get a unique group address across the network and be able to rendezvous receivers and sources. I'm showing 5 nodes here. You'll see the 3 receiver nodes on the right-hand side. They're going to run an application called GAP Receiver, which they're simply going to join the group that hashes from the group name PIM-MBONE-group. Let me start this one up. So this guy is joined. And I'm going to join receiver 2 and receiver 3. So they're just waiting for messages to come in. On the left-hand side, these 2 windows are 2 senders, individual senders that will send to the same group name. Note the group name is PIM-MBONE-group, and the sender is going to send a message, a text message, multicast anywhere, and it's going to send it to the same group address that the 3 receivers are joined through. So let's start that up. And we see that the hashed group is 224.254.10.50, and that's the same group that the 3 receivers had joined, and therefore you see them receiving the messages on the right-hand side. Every message will have a sequence number, so you see that they're individual messages and they're continually being sent. Okay, now what I'll do is I'll also start up another sender here on the left-hand side, and we'll have it send a message called multicast everywhere. And of course, it's going to send it to the same group. The group name is PIM-MBONE-group, and it will hash the same group address. So let's start that up. And you see that it is hashing to the same group. And then you see the receivers on the right-hand side are getting interleaved messages from the source that's sending anywhere and the source that's sending everywhere. Okay, if we stop this source here, we'll see we're just getting messages from the first sender. Okay, and if I stop the source here, you'll see no messages being received. And then I'll just start it up again, just to show you that there's new sequence numbers starting. And that's basically the application demo. If you stay tuned for the second part, you'll be able to see what's going on under the hood in the protocol demo. Thank you. Any questions on that? Okay, let's go to the protocol demo. We good, Lenny?
Yep.
Okay.
and I'm about to give you a GAP protocol demo. This is the second part of a two-part series. The first part was a demo on a GAP set of applications with no detail on protocols. Here we're going to give you a detail on the protocols. So to start off where we left from part one, we had 3 receivers on the right-hand side and 2 sources on the left-hand side. What I'm going to do for this demo is fire up this receiver and log protocol events. Now, it turns out that we're going to join a special group name called Collision PIM-MBONED group, and that's going to force a collision to happen from this source over here. It's intentional, so we can show collision detection on a hashed group. But let's first start up this guy, and it will be doing some GAP logging. So wherever you see timestamps, these are messages coming from the GAP API, and otherwise they're messages coming from the application directly. So for this guy, he is IP address .5. So let's start him up, and we can see the messages received on the monitor. We see .5 sent a claim message, and this guy received it. And they claim that the PIM-MBONED group name hashes to 224.254.10.50. That is correct. We stored a state and we detect that there's no collisions. We'll do the same thing here for this receiver. This receiver is .6, and we'll start him up, and we'll see that this node received from .6. It hashed to the same group that the other node did, and so there's no collision, so everybody's doing just fine. Let's go ahead and start up the source, which will hash to the group, and we'll see that the source is .8. Let's start up the application there. And we see that .8 came in just like the other 2 nodes. Everything's good. We see the 2 receivers running just fine. Okay. Now note that these 2 receivers are joined to PIM-MBONED group, and this guy up here is joined to collision PIM-MBONED group. And so this source, what we're going to do here is put logging on this source, and we're going to have it send to the collision group. And the reason we're going to do that is because it's going to start sending on a bad group name. So this is just a fictitious group that is going to hash incorrectly, okay? And as it turns out, when you come up here, you see that it was received by 7, which is the source down here, and that they claim that it was this erroneous group 224.255.255.255. We said that it was an illegal hash because the hashes must be one of these 4 hashes. We tried 4 times to find a unique hash for the group. So if, for example, it was a correct hash, say the 91, but there was some other group name that hashed to the same group, then a claim would be sent back with the second one. And then if that collided, then the third one and the fourth one, and so on. So we're thinking at this point that since this .7 node hashed to this address here, that it's really a bad actor because it didn't even try one of the 4 good nodes, okay? So we immediately send a claim back, and what we do is we claim that the real hash is 91, which is the first one here, and we send that out. Now, when this guy received it, we go back to where it collided. The .4 node, this guy up here, he said he's going to claim the correct address, and this guy detects a collision erroneously. Okay, he believes there's test code put in to the application to believe that 224.255.255 is the real group. So this guy thinks that .4 has collided. So what he does this time is he's going to rehash using normal code, and actually hashed to the same group address. And now he's a happy camper, and he goes ahead and he starts sending to the new group address, the 91. And when you see that, if you come down here, you see that this receiver that's joined to this address is the correct address is starting to receive application packets. And by the way, while that's all going on, this other group is just running just fine because it's completely unaffected. Anyways, thanks for listening. That's the end of the protocol demo.
Okay, so any questions with that? Okay, so just to wrap up, I wanted to make a quick point about collisions. We did some simulations for a 24-bit unique width hash, and we ran 1 million groups, and we found that there's a 2% chance of collision. And if you look at the right-hand side above, you could see that most of the collisions, 28,000, happen with one collision, 500 happen with two collisions, 8 with 3. Now note that this simulation was going through 1 million group names by incrementing the character string at the last octet. So they weren't random, or they were very similar type group names. So if you, I'll do a simulation with some arbitrary group names and see if this rate goes down. But 2% out of 1 million is I think is pretty small. Then we ran it for 10 million, which is below, and it moved up to 20%. But note, if we do it for IPv6 over 10 million nodes, that percentage is going to drop significantly on using 32 bits. So that's kind of what's motivating. So the point of the slide is that collisions are very real, and we may not even have to run the collision detection machinery at all, because the hashes will go a long way on creating groups that are unique. Next steps are we're going to do more testing, of course, to try to find corner cases, add some more security features, especially if you have to rekey. How do you rekey in a decentralized environment, and who do you trust, and how do you actually distribute the new encryption key to? So there's a multi-party computation algorithm called Shamir's algorithm, where you can transmit part of a key to multiple nodes. Uses a polynomial math to be able to obfuscate and fragment the key, but it can be reassembled by the receivers that you want to send it to. So if necessary, you can unicast these things to who you believe are the good actors and leave the bad actors out. And we can then rekey if necessary. Not sure this is necessary, but these are things that we're thinking about if we have to rekey. The most important thing is I want to test on overlay, and I'll use a Lisp overlay to see how this works. So I'll put some nodes at my house, I'll use my laptop, I'll use some AWS VMs, and have all this run over Lisp multicast, and we'll see the GAP protocol, and then I'll be able to report on that in the next IETF. The jury's still out on the code, the lightweight RESTful API, because it's really, well, at least it's important to me that this becomes centralized. Decentralized. Let me reemphasize that. I want this to stay decentralized because it's more plug and play and it's more fair in this centralized world we're starting to see more and more. Maybe write more apps if there's anybody out there that wants to write apps. I know Nate's application or use case, the apps are written in C, so maybe on the to-do list is write the protocol in a C API, and so that'll go on the list as well. So, and just seek more developers that want to play around with this stuff. That'd be great. Just contact me. There are a few guys that were involved in this that ran some ideas, mostly Nate and Chris Hops. Thank you for that. And if you guys want to watch the demo, just grab those QR codes and you can watch the demo. Yes, questions?
Sunny Zhang ZTE. I'm not saying I will do the APP. I just want to comment for the protocol. I think this protocol is well designed because every aspect I thought it has been writing in it. So I think it's good. And I have a question. Maybe Stig has mentioned before. I'd like to know if the link local address will be assigned, or just site local or global local address will be assigned.
My intent was it to be global, a
Global.
global address, and Stig just brought it to my attention that I made a typo in the spec and used FF02, which implied link local. So I apologize for that.
Oh, yeah.
So I plan to use FF01. Do you think that's okay?
Okay,
Yeah.
just global.
Yeah,
Local
and the
address.
reason why also, it's just not a question between link local or multi-hop. If it's going to run on an overlay, most overlay nodes, you don't know where they're going to pop up, and it's most likely a global scenario anyway. So you want to be consistent with the scope of where the overlay is going to be as well.
Seems like in the use case, link local address can also be used, right?
Sorry, I didn't get it.
Because in the arrow situation,
Yeah.
a link local address can also be used, right?
Oh, yeah. Link local could be used if
Yeah.
the overlay is doing a layer 2 overlay. Yes.
Yeah.
Yes.
So if it will be
So it would
considered-
work in either case. Yes, but in the case where we don't use an overlay and we want to use layer 3 native multicast, we have to use a global address because the gap nodes have to travel across a PIM domain or something,
Okay.
right?
Oh,
The allocation protocol has to run over the PIM domain.
thank you.
Yeah,
Hi,
this
Stig.
is Stig again. Hi. Yeah, I asked you about doing the same message for V4 and V6 allocation. Are you sending the same message over both V4 and V6, or you're just choosing one of the protocols?
It needs to go over both.
Yeah.
Yeah.
So,
I mean, it can go over one, either or both. So,
yeah. No,
and I'm
that's
not
right.
sure, since we don't want to configure anything, it needs to go over both.
Yeah, no, at least what I realized is, you might have some hosts that only support, say, one address family, right? So if you send one message for both, then, some hosts might only support the other address type and
Yeah.
never see those messages.
Okay, so I'll make sure it's clear in the spec that we send 2 messages and we make it, we make it robust for that. Yeah.
I know it's kind of, the main thing is to test how this protocol works and stuff, and these are details
yeah.
you can sort out later too.
Yeah, I mean, if we don't send 2 messages, then we have to figure out who's who, and there's more delay in figuring out who wants what, and it just adds all this complexity to the protocol. So why do that? So yeah, good comment. I'll make sure I update that. Hi.
Hi, Dino. Nice to see you again. I still have a question because just now you mentioned that there's about 2% of collision rate when you just simulate in about 1 million data size. So I think maybe it's better to provide more sets of different types of or different amount of the whole amount of the data. It will be better because we can see, for example, if we set about 100 groups, how many of them will be cleared.
Yeah, I think we have a lot of flexibility with IPv6, and if we think this is going to run mostly wide area, what I've seen working at Cisco and doing multicast over the years is that if you do a lot of wide area multicast, the switches will do don't have to do they do IGMP snooping, but there's less collisions that happen on wide area than it happens locally because of the type of applications. And the other problem is the group allocation was always ad hoc in the past because network administrators would decide, and then they would learn that snooping was failing because of the overload, that then they would have to pay really close attention. When I worked at the NBC Olympics and we did multicast there, they basically signed the low order 3 bytes of the multicast address with the same 3 bytes of the source, because it was always one source would send to the multicast group. It was always one to many. So they did that for ease of network management. When they looked at a group, they knew it was long jump or versus track and field or something like that. And so they just decided to keep it a simple mapping. And they did assign the source addresses of those sources where the low order 23 bits did not collide because they wanted just to avoid the IGMP snooping problem.
Yes, that was my question. Yes, I was wondering why can't we just avoid that question by configuration deliberately? Okay.
Yeah.
So
So I mean, it's when you say the thing's going to be zero configuration, you have to really make your design respect that point. And so we're going to have to, it's going to have to be an architectural constant. But I don't see any reason why we use 23 bits for IPv4 and 32 for IPv6. And we know IPv6 will have less hash collisions and V4 will, you know, the problem is I don't know I mean, maybe Stig can comment on this. I don't know the state of multicast in general in the industry where if people are moving from V4 multicast to V6 and we're seeing more V6 applications pop up, but not sure.
okay. So another question is that when a collision happens, how long will it take to solve the collision?
No more than 1 second, because when everybody sees the claim message that collides with an address collision, all the members all the nodes that are part of that group name will set a random delay timer of 1 second, 0 to 1 second. So it could be as fast, and I think I put a little jitter of 100 milliseconds. So between 100 milliseconds and 1 second is a timer will expire for one of the nodes. And that one, when it expires for that node, they send the claim message, everybody receives it. And if their timers are running, they cancel it. So it's only one node that will send it within 100 to, I think it's actually 100 to 900 milliseconds, because I did a 10% jitter of that a little bit as well. So I'm playing with the timers just to see how it works out. So less than a second to resolve it. Yep.
Okay.
With network propagation time that has to be added to it as well.
Okay. Okay. Thank you.
Yeah, thanks.
This is Nate again. 2 comments. One, the zero configuration came from our requirements because our users don't know how to configure stuff. And the other one, so you mentioned that you wanted to do global scope, but that's FFO1. Is that FFOE or what's?
I think it's FFO1, if I recall. E is global. Okay, E is global. Thanks. I'll go read my IPv6 documents and make sure I use the right one. But thanks for the correction. Yeah, okay. Okay. That's it. Any other questions, comments?
So what is the status of the document? Has it been adopted? And it's I assume you're looking to adopt this in PIM, and has it gone for an adoption call or plans to?
Yeah, Mike and I requested the working group to consider it. And Stig, do you want to?
Yeah, so I honestly don't remember exactly what I said in PIM yesterday, but yeah, we might do an adoption call on the list. At least I think it's in charter. It's something we seriously should consider doing in PIM. But yeah, I don't see any urgency in adopting it though, right?
Yeah,
I
agree. There really isn't urgency. We could have a couple more revs of the document and some more presentations and see where testing takes us. And see,
But I think one thing we need to think about is, relationship with your document versus what Nate is doing with his stuff. And do we want to adopt both in the working group?
Yeah.
Or do we want to?
I think we're trying to figure that out as co-authors as well. So, yeah. Okay, thanks.
Okay, yeah.
All right, Prasad, if you'd like to. Prasad, would you like to drive the slides yourself, or do you want me to drive?
Go ahead, please. Go ahead and share it. So yes, thank you for taking this item. Good afternoon, good morning, good evening, wherever you are. So basically, this talk is about enhancements to signal-free list multicast, co-authored with Dino and Ashwin. This was presented at the LISP yesterday, so but Dino had already suggested that we present this at MBONED as well. So next slide, please. Yeah, thank you. So the problem statement is essentially very straightforward, meaning at least to people who have looked at it, essentially the 8378, the signal-free RFC, that is the Lisp signal-free RFC, defines pretty good mechanisms for having multicast traffic between Lisp sites using a ingress replication that is a unicast based underlay, and that has good semantics essentially for receiver sites joining a particular group or leaving a particular group, either using V4 or V6, and then that getting propagated into the map server where the such join requests are collated or consolidated, and then essentially a consolidated replication list is constructed, and then it is sent to the ingress ITR, that is the head end where the source is connected or hosted on the Lisp site where the source is hosted, and essentially good procedures are defined. But all of this is only possible with a unicast underlay, which is a very good starting point. But the as kind of things scale, then we go into situations where we would want to, as the larger the number of Lisp sites increase, then we would want to take advantage of multicast replication in the underlay, and this has also kind of led us to think about using the underlay multicast capabilities while still keeping the backward compatibility, still maintaining the backward compatibility, because that is a very important point. And another dimension of this is essentially the different address families. Some of the sites may use a V4 underlay, some of them may use a V6 underlay. They could be coexisting. So those considerations have to be taken into account as well. So that's kind of the overall background where we started, or why we started thinking about this problem. And of course, the draft tries to probably give some solutions in that direction. Of course, it's not complete; just made a start, and we hope to get some feedback and try to refine the proposal and go ahead. Yeah, next slide, please. So yes, so I'm sorry I did not include a terminology slide, but most of the terminology that we have used here in the draft are from the 8378. We have been trying to be consistent with 8378, terminology and syntax / semantics. So we don't want to kind of put anything new. Of course, augmentation is also fine. But so the only two terms that we would want to augment or add is essentially whenever we refer to the S comma G state, that is the SEAD comma G state, then essentially we are referring to the overlay multicast. That is essentially the overlay multicast source and the overlay multicast group. And there could be essentially requests coming in, the IGMP or MLD requests coming in from the endpoints to the egress Lisp site, which will in turn essentially take that and try to construct some Lisp PDUs that we define, that is the TLVs that we define in this draft, and convey to the map server that the intent, that is the interest for the SEAD comma G. And whenever we refer to the SRLock comma G, then we refer to the underlay multicast, that is the multicast state for the underlay. So the idea is essentially to not use a protocol like PIM, but use the signal-free semantics, but to essentially convey the interest that the overlay that is the clients have, that is the Lisp clients have, and tell the map server that there are Lisp sites where there are interests for the multicast SEAD comma G state, and that will in turn cause SRLock comma G state to get created, because the trees are required to anyway be transported over the underlay. Now, as I mentioned earlier, we want to all support a mixed mode where you have both unicast and multicast that is capable in the core. That is certain Lisp sites have capability to receive unicast or multicast or both, but certain have unicast only, and therefore we want to keep it. And of course, the subset of that is essentially the multicast only underlay case where everybody talks to the underlay multicast. Of course, the another subset which is missed out here, sorry for that, is the unicast only, and there are no extensions really needed for this, but whatever schemes we use here does not prevent that backward compatibility. So that's the kind of the overall scope. And of course, the mixed RLE, the objective of the draft is essentially to construct a replication list entry. Thanks to Dino for really putting this in a mathematical way, where the idea is to essentially given a SEID and a G, right? Then you construct a replication list, which is nothing but a set of tuples, where each tuple is essentially either a SR lock, G, or a SR lock, UR lock, where the difference between the green and the blue essentially is that the green represents the space where the R locks are capable of receiving multicast traffic, and therefore they use the multicast group in the underlay, whereas the blue ones essentially represent the space or the set of sites which are not really capable of receiving multicast traffic in the underlay, and therefore they would still continue to receive traffic in the unicast underlay. So and as when those sites migrate, then essentially you would have the RLE, the greens, the blue sites collapsing into the green, and that can sort of migration, eventual evolution can happen over a period of time, and this kind of would probably even help customers where they have you don't have to increment, we don't have to upgrade all at once, but incrementally upgrade over a period of time. I think that's the idea. And of course, what we have not included are layer 2 underlays, where Lisp provides the layer 2 underlay. I mean, it does provide this Ethernet as a service, which we have not considered here, or any other underlay like BR or MPLS. We don't want to, I mean, rather, we have not covered it in the draft. It's not that we don't want to, we probably don't cover it in the draft. And of course, we don't have any mechanisms to compute the underlay multicast group. They could use any kind of a hashing function or any lookup mechanism where the previous work that was presented had very good mechanisms for group allocation, which which are not covered in the draft. So essentially, we don't talk about any such things. Next slide, please. So yeah, so in terms of the procedures defined in the draft, very similar to the 8378, we kind of split the procedures into three different aspects. I touched upon it a little bit briefly. So essentially, if you talk about the receiver side procedures, we would have the IGMP join coming in, or the MLD join coming in from the endpoints, that is the Lisp clients, and then the egress Lisp sites would get them and then map it to whatever instance mapping that they have. And that would essentially then result in taking that join or the interest and conveying it to the map server using the formats. Again, the formats are kind of called out in the draft. There is nothing new that we probably need. Most of it is already there in the 8378. We're kind of only giving the procedures, but essentially there are two or three aspects here. One is the aspect being, the join/leave semantics have to be taken from the 8378. The only addition here that we really need is essentially the ETRs, that is the egress sites will tell the map server that I need the overlay multicast being transported in a particular underlay group. So the mapping is already been done in the egress site, and then the egress site based on its policy or whatever its algorithm kind of determines the underlay group and communicates it to the map server. And naturally, the next logical step is essentially the consolidation of such replication lists from different egress sites. The map server will take them all. Some of them can be unicast, some of them can be multicast, and combine them. And of course, there are certain bits, the merge bit that we use to tell the map server that we don't have to ignore or override the later one with the previous one. So it kind of merges them and consolidates it, and at a later point of time, when there is a site where you have a source connected, then the source site will essentially get it via the from the map server, the list of the sites, that is the list of unicast sites receiving or requesting unicast traffic, and then the sites list of sites that are requesting it in the multicast. That consolidated list will be obtained from the head end site, and the streaming will start and kind of go over as new sites join. They may request additional copies or rather additional RLE elements, which could be either unicast or multicast, or sites can go away and therefore that list should be kind of maintained over a period of time, and finally when all of them goes down, then the kind of tear down happens. So that's those procedures are not so clear in the draft. I would say, definitely more work needs to be done. It's the 0.0 version, but I thought, we made a start and then probably get some feedback and kind of refine it over a period of time. So that's mostly what I wanted to cover. Yeah, the reference model is just there for any discussions we want to use examples. I think I'm mostly done. Probably any questions I'll be trying to answer. And
Dino, you're up. Looks like you have a question.
Hi, this is Dino. Prasad, I don't know if you were at the end of the LISP working group yesterday, but Daryl made a pretty good comment about we kind of enumerated all the combinations of using underlay groups and underlay unicast RLOCs, but he made a comment of what if some of the members aren't on the overlay at all, and
yes.
And if that happens, we actually need to encode the replication list to say we then have to replicate natively, in other words, to an underlay multicast group directly. And what that means is even though the group RLOC is in there, the packets that go to that group are encapsulated list packets where we'd have to send to the exact same group again that are unencapsulated so they could make it to the non-overlay nodes. So I think it could be done, but I think we might need a bit, and I haven't looked at RLE in a long time, the format of an RLE entry, but we might need a bit in the RLE saying forward native don't encapsulate or something like that. So that's just an FYI. So that's an action item for us to go off and look at and put text in the spec to deal with.
Sure, Dino. I'll note it down and I'll do the homework and get back to you.
Thanks.
So what was the outcome of LISP? Is it is this looking for adoption in LISP, or are you looking for feedback from MBONED?
Yes, I would think so. Mostly this would be in Lisp, if I'm not mistaken. Stig is also here. There is definitely overlap with PIM, Lisp, and MBONED, but I thought we will start with Lisp because yeah, I guess that's probably a decision for the Lisp/PIM chairs, whether this should go in Lisp or PIM.
As Stig here, to me it seems clear that it should be done in Lisp. It's pretty heavy on the Lisp, but yeah, we'll see.
Sure.
There seemed to be a pretty good interest in the Lisp working group yesterday, I thought.
Thanks. Any other questions for Prasad? Great. Thanks for sharing.
Thank you. Thank you.
All right. Our final talk will be on TreeDN, which is tree-based CDNs for live streaming to mass audiences. This is a draft that since IETF115 was recently adopted in the MOPS working group. And the MOPS working group, they had the suggestion of the draft is intended. It utilizes multicast components that we're all familiar with, but synthesized in a way that can be useful for the media ops group. And some of the suggestions from that working group was they would love more feedback from from MBONED to help review some of the multicast parts of the draft. So what is TreeDN for those who don't remember? it's addressing the problem of network resources being consumed by live streaming, specifically with as live audience sizes are kind of exploding, and you combine that with the increasing bit rates for things like 4K, 8K, and augmented reality. We may be at an inflection point, and the question is, are we at this inflection point? If not now, will we ever be? And if the answer to either of those questions is yes, then the question is, well, what should we do? And so that's where the concept of TreeDN comes from. The other thing is, for those folks who think, well, live streaming is not really any different than on demand. Live streaming has some fundamental differences than on demand streaming, in that there's expectations for much lower latency when it comes to live streams than on demand streams. You can't just stream it have a minute or two play out buffer, because you run the risk that your neighbors or the bar across the street, everybody's cheering for the game-winning score, while you're a minute behind. Also, join rates are vastly different. There's in on-demand video, the rates grow significantly in the course of a night, but they're predictable and kind of gradual and smooth. Whereas with live stream events, you could have millions of viewers joining a couple minutes right before the game time starts. So the idea of addressing this problem with network-based replication is obvious to us, of course, but multicast has been pretty successful in a number of places. Things like financial networks, it's absolutely vital. But when it comes to internet over-the-top multicast, hasn't obviously been very successful. So it's worth looking back at what went wrong. And there's kind of the three main problems of internet multicast were the all or nothing problem, where every single layer 3 hop between source and receiver must be multicast enabled, is a pretty significant barrier. Essentially getting every single interface on every single router and firewall on the internet to support a multicast routing protocol is a very high bar. V6, by the way, has the same exact challenge, and you can see why it's also struggled with widespread, ubiquitous deployment of the past few decades. There's the complexity problem, where the perceived benefit has not been seen as worth the cost of deploying, managing, and troubleshooting and operating a multicast network. And then there's the chicken and egg problem of that there's no multicast audience because there's no multicast content, and vice versa. So the good news is that, and this isn't, this should come as no surprise to the people in this room. The folks in this room know and understand this better than anyone. But there are technologies out there to address each of these problems. So we're kind of at an inflection point on the supply side. And specifically, what are those things? So TreeDNs, tree-based CDNs, it essentially leverages native and overlay concepts to deliver a service that addresses deliver a service over the internet that leverages multicast and addresses those three fundamental problems that have hindered multicast deployment previously. So there's the native component on net, and the idea there is simply to just use SSM. It turns out that most of the vast majority of the complexity of multicast comes from ASM, and if you just use SSM, you radically simplify a deployment. You can get rid of, say, 90% or so plus of the complexity problem. Typically, we're not prescriptive, it's kind of late, forgetting which one's the right word to use now, but usually, SSM usually uses PIM SSM, but could be any technology that can deliver SSM services. And combine that with so SSM is used in the native part of the network, and to reach receivers who are on unicast only networks. That's where overlays come in. AMT is the is the typical protocol that is technology that is used here. Could be any overlay technology, but AMT kind of is the most obvious candidate here because it integrates well into the application layer and the end host, and it's dynamically built tunnels. So AMT solves the last mile problem and enables receivers on unicast only networks to be able to receive multicast content. So, in that way, it addresses the all or nothing problem. You now don't need every single hop supporting multicast. You can just tunnel over those parts of the network that don't. And the parts of the network that do enjoy multicast, that have deployed multicast, get to enjoy the benefits of multicast. It also addresses solves the chicken and egg problem because with AMT, pretty much every internet user becomes a potential viable multicast audience member. Again, in the past, it was difficult to do incremental deployment. It was kind of, like we said, the all or nothing deployment. But this architecture enables incremental deployment, and as I mentioned, the parts of the network that are multicast enabled enjoy the benefits, and the parts that aren't just get tunneled over. And most importantly, end users receive and enjoy the service. They don't have to depend or coordinate with their last mile provider or cross their fingers and hope their last mile provider supports anything. So, it's really just SSM plus AMT. And this diagram kind of illustrates that. You have the big I internet, and some subset, some portion of that network. A treaty is the treaty end provider, is multicast enabled. You have a content provider that is delivering content, which delivers it natively to native receivers who are on net. And for receivers that are off net on unicast only networks, that traffic gets sent natively to the relay, which an AMT relay, which sends it via AMT tunnel to the receiver. So that's if you look at traditional CDNs without multicast, there's different CDN models, but one of the most common one is you have a bunch of CDN boxes that get deployed in a network, and you send content to each of them, and they handle local replication. By contrast, if you compare that with CDNs with multicast, which is treaty ends. One, we renamed that CDN box. It's now an AMT relay, and it can be much closer to receivers, and traffic only gets sent to relays that have interested receivers locally. And most importantly, the real value here is that CDN box is no longer, some x86 rack of servers that needs to be powered, racked, stacked, and plugged into revenue generating ports on routers. If the infrastructure and say the routers support AMT natively, essentially you've got a CDN on a chip. You can deploy a network provider can provide CDN services at essentially zero capex. It's just a couple lines of config to enable, and you've got a CDN on a chip, and it costs nothing to offer the service. You can even argue maybe zero OpEx too, because it really doesn't. You don't have to take up an additional power or space. So that's the benefit to service providers. you get more efficient network utilization. And it's not just about scaling for, existing content. It enables new content that perhaps isn't possible. That the internet has got along just fine thus far with brute force unicast, but the question is, how far can brute force unicast go? This fall we saw, Thursday night NFL football with, the first week had, I believe it was 12 to 13 million simultaneous viewers. What happens when they're all 4K, or what happens if you want to do an AR, live streaming AR with a 1 gig stream, for example, to hundreds of thousands of viewers, or maybe millions of simultaneous viewers? Is the internet up for that? At some point, does brute force unicast run out of steam and you have to do something else? The other benefit is it allows service providers to offer replication as a service, kind of a new service, and potentially at zero additional cost to deliver this if their existing infrastructure already supports AMT natively. And it's also an open standards-based architecture using widely understood and available protocols, as opposed to most traditional CDNs are proprietary and not interoperable. And it also is far less coordination between the content provider and the CDN. You don't have to worry about storage, data storage and protection, key management. Essentially, a TreeDN is, a provider that is delivering TreeDN services, just pushing packets. And all of that stuff, that transport stuff, gets handled by the endpoints, the source and the end receiver. It's also democratizing and decentralizing technology. Is it healthy for the internet and society that only a handful of companies kind of control nearly all content distribution? TreeDN kind of addresses that. So I focused on live streaming and video, because that's really the most exciting and sexy use cases. But it's really about any multi-destination content. Could be the least sexy, but probably more tactically viable use cases, large file uploads, large file downloads, OS upgrades, stuff like that. And that is that's something that kills networks today. So kind of summarize, we may be at a point where supply and demand curves are crossing. So, demand meaning the demand for network resources because of live streaming. Up until now, maybe we haven't needed multicast. Audience sizes, live audience sizes weren't big enough, or bit rates weren't large enough. But now we're beginning to see them, tens of millions of simultaneous viewers of stuff at really high bit rates. So the demand is there, and the supply, previously we had a alphabet soup of multicast routing protocols, and that kind of blew, for people who aren't in this room, they found it to be way too difficult to manage or care about. But now, with ASM and SSM, all the other stuff isn't necessary anymore. So, that's what TreeDN is designed and optimized to deliver. So the feedback from MOPS on Monday was, they gave some suggestions. The biggest questions that came up were mostly transport-related issues that have to do, they really aren't multicast issues, they're really TCP versus UDP issues. There are a lot of things that CDNs enjoy that come from TCP, things like, packet loss and resiliency and, handling loss and reliability, visibility of packet loss, encryption. How is encryption handled in a multicast environment? It's been done, but I think it's far less understood. Authorization and billing. How exactly does the billing work, or how could it work? It's certainly possible. It's a slightly different billing model, but it's something to call out. And things like ABR. This is something that comes naturally with, and it's a vital service in CDNs. how to do this with multicast. The short answer is, well, just have different groups with different bit rates. And the question of, multicast over quick, this is something that there was a draft, or there is a draft out on this, and it's probably really worth, pushing that and driving that, because that can address a lot of these things. So, part of the challenge for us is to determine the scope, what is in scope and what is out of scope. What the thoughts are for most of these. The draft is kind of very layer 3 focused, but for transport related issues, we plan to at least call them out. Maybe not necessarily provide solutions, but just say these are the gaps, these are the things to be aware of, and maybe call for additional work. But the part for MBONE-D, the reason why we're speaking about this here is that, like I said, MOPS would love additional review from the multicast experts. So please encourage folks to read and provide feedback on the draft. Be happy to take any questions that anybody might have. Okay, looks like there's no questions. Any other questions or items anybody has about anything? Jeffrey?
Lenny, one question about 3DN.
Mhm.
Have you ever thought of working with the what's Lead Echo team to try to broadcast a few small sessions like MBONE-D session itself using 3DN?
We have spoken. I don't know, Lorenzo, are you listening? What do you think? But yeah, the short answer is yes. We have communicated with them. They have some infrastructure. They have used multicast in the past. They actually spoke at MBONE-D, a couple meetings back. They would love to leverage multicast technology in their deployment. They have some challenges, as I recall, with the cloud providers that they use don't support multicast. But yes, we would love to. And thanks for reminding me. I'll ping the team again.
Well, I guess if we cannot get it working here, it's not going to happen elsewhere. So maybe start here is like maybe throw in gap as well.
Well, our hope is to start with NFL football or something even bigger than IETF meetings. But yes, IETF would be a great place to dog food this technology. Any other questions on 3DN or anything related to MBONE-D? All right, and thank you, everybody, and we'll close the meeting, and we'll see you next time. And thank you, Stig, and thank you, Nate, for taking notes. Stig for standing.